Now here the question is, an is a sequence of real numbers satisfying an+1 equals 3an upon 2+an. We need to prove that if a1 lies between 0 and 1, then the sequence is increasing, and if a1 is greater than 1, then the sequence is decreasing. And hence we have to prove that this limit n tends to infinite an is equal to 1. Now what we are given is, we are given that an+1 is equal to 3an upon 2+an. Now since each of the case a1 is greater than 0, we can say that any an+1 will be greater than 0. Now we can rearrange this as 1 upon an+1 will be equal to 2+an upon 3an, and we can also write this as 1 upon an+1 will be equal to 1 upon 3 plus 2 upon 3an. Now what we'll do is, we'll subtract 1 both sides. We can write this as 1 upon an+1 minus 1 will be equal to 2 by 3 1 upon an minus 1. So we have this relation which is an+1 minus 1, and it will be equal to 2 by 3 1 upon an minus 1. Now using this recurring relation, we can prove that 1 upon an+1 minus 1 will be equal to 2 by 3 to the power n 1 upon a1 minus 1. Now we'll take this first case when a1 lies between 0 and 1. Now if a1 lies between 0 and 1, then 1 upon a1 will be greater than 1. 1 upon a1 minus 1 will be greater than 0. If 1 upon a1 minus 1 is greater than 0, then from here we can say 1 upon an+1 minus 1 will also be greater than 0. So this expression will be positive, and this expression also will be positive. So we'll start with this one. We are given that 1 upon an+1 minus 1, and it is equal to 2 by 3 1 upon an minus 1. Now it will be less than 1 upon an minus 1. Now if we compare these two, we'll get 1 upon an+1 will be less than 1 upon an, and since each term in the sequence is positive, we can say that an+1 will be greater than an. That is, this sequence an is increasing. So we have proved that this sequence is an increasing sequence. Now for the second part, if we take a1 greater than 1, so if we take a1 greater than 1, 1 upon a1 will be less than 1. That means 1 upon a1 minus 1 will be less than 0. And if 1 upon a1 minus 1 is less than 0, then 1 upon an+1 minus 1 will also be less than 0. Now for this case, both these expressions, they will be negative. So we are given that 1 upon an+1 minus 1 will be equal to 2 by 3 1 upon an minus 1, and will be greater than 1 upon an minus 1. Now again comparing these two, we'll get 1 upon an+1 will be greater than 1 upon an, that is an+1 will be less than an. That is, when a1 is greater than 1, then this sequence is a decreasing sequence. So in the first case, when a1 lies between 0 and 1, the sequence is increasing, and when a1 is greater than 1, the sequence is a decreasing sequence. We can also write that this an+1 is 3an. Now we'll add 6 and subtract 6 upon 2+an. Then this an+1 will be 3 minus 6 upon 2+an. Now this value will be always less than 3. So an+1 will be greater than 0 but less than 3. That means terms of the sequence, they are bounded. So the sequence is monotonic as well as bounded, then using monotone convergence theorem, we can say that it must converge to some limit L. Now in both the cases, we need to prove that limit of the sequence is 1. Using recurring relation, we can write 1 upon an minus 1 will be equal to 2 by 3 to the power n minus 1 1 upon a1 minus 1. Now if we take this limit n tends to infinite, this limit will be 0. So we can write limit n tends to infinite 1 upon an, it is equal to 1. So from here we can say this limit n tends to infinite an will be simply 1.